Hi everyone, now we are at sequences and series, lecture number 9. I start the session with some random doubts from the students. See, most of the students are asking about this kind of questions. See, about the convergence of the series. For example, series AN, okay, and why we have to take a sequence of nth partial sum, why it is taken, why it is required. See, I told you already, you generate a special sequence. S1 means A1, S2 means A1 plus A2, right? A1 plus A2, and S3 means A1 plus A2 plus A3. Why I am defining like this? Some students are asking, so why you are defining like this? Why? Because, see, what I want what is series A, and that means what is the sum of this one, right? You write this one, what is mean by series AN? Series AN means A1 plus A2 plus A3 plus up to so on. Here series nothing is given means n is equal to 1 to infinity. Okay, up to so on. The last one, let's say it is A infinity, the last one possibly. So how many terms are there? Infinitely many terms are there. Okay, actually I want what is this sum. Now if I generate my sequence like this, okay, if I generate my sequence like this, and now this is sequence of nth partial sum. If I say this sequence is convex to some L, what does it mean? What is the meaning of this? That is limit n tends to infinity. Sn is L, right? Sn is L. Its meaning, right? Again, what is the meaning of this? So its meaning is, listen carefully. Again, what is this? This meaning is S infinity is infinity, right? Indirectly, S infinity is L. Sorry, limit n tends to infinity. That means what S infinity is equal to L. What is meant by S infinity? See, S1 means first term, S2 means sum of first two terms, S3 means sum of first three terms, S infinity means sum of first n term, sum of first infinity terms, right? A1 plus A2 plus A3, right? Plus up to so on plus A infinity. This is S infinity. This is what? This is S infinity, right? According to definition, according to our sequence of nth partial sum, Sn definition is that. Therefore, finally, indirectly, Sn is L means what? So S infinity is L means, so this is L. That means what? Indirectly, you are getting sum of all these numbers, A1 plus A2 plus up to so on plus A infinity is equal to L. Indirectly, this is series. N is running from 1 to infinity, An is L. That means what? Indirectly, so if the sequence of nth partial sum is converging to L, indirectly the series also converging to L. That's why we are taking this kind of sequence. Hope it is very clear. And most of you are asking this question. So sequence 3 plus 1 upon n. Is it converges? Yes, it is converges to 3. You apply limit. So limit n tends to infinity. Okay. 3 plus 1 upon n. Now what is this value? This value is 3. So therefore this is finite number. Therefore the corresponding sequence converges to 3. Okay. So this is about sequence. Same thing if I write in series. So same thing. Let me write in series. So series 3 plus 1 upon n. 3 plus 1 upon n. N is running from 1 to infinity. Now what is the first term? First term is 3 plus 1. Okay. Second term, substitute n is 2. 3 plus half. Okay. Third term, 3 plus 1 by 3. Fourth term, 3 plus 1 by 4. So plus up to so on. How many terms are there? Infinitely many terms are there. But infinite times 3 will come. So 3 is coming first time, 3 is coming second time, 3 is coming third time, 3 is coming fourth time. Likewise 3 will come infinite times. That means 3 plus 3 plus 3 plus 3 plus 3 up to so on how many times? Infinite times 3 will come. Forget about what is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. That is later. But this will become infinity only. Because 3 into infinity, right? 3 is coming infinity times. So 3 into infinity is infinity. So therefore sum become infinity. Therefore, what can I say? This series is diverges. So therefore, this series is diverges to infinity. Sequence is different, series is different. Likewise, you look at every constant sequence. For example, 2 is a constant series. It is diverges to infinity, right? Because 2 plus 2 plus 2 plus 2 plus, how much you get? 2 into infinity will get, that is infinity. But if you look at sequence, constant sequence comes to 2 only. Why? Because limit n tends to infinity a and I want. Instead of a and you are having 2. What is limit n tends to infinity to 2 only? It is a finite number. Therefore, sequence comes to 2. But series diverges. Hope it is clear now. And you are confusing with uh, this kind of issues also. Let me discuss here. For example, yeah, I will discuss this later. So, for example, if you are having, see, nth term of a sequence is 1 plus 1 upon 3 plus 1 upon 3 square plus 1 upon 3 power 3, right, plus up to so on, plus 1 upon 3 to the power of n. This is an. Then corresponding sequence, most of you are writing like this. 1 by 3 power n only you are writing. But this is absolutely wrong. Then if you are writing like this, then what is an? An must be only 1 upon 3 power n, right? But what is an? An is this entire thing. Therefore, you must write like this. You must write like this. So, series an is, sequence an is nothing but 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 to the power of 3 plus up to so on plus 1 by 3 to the power of n. So, this is a sequence actually. This is correct. This is correct. You should write like this. This is sequence. What is the difference between this one and this? Difference between these two is, see, if you look at if this is your sequence, then what is a1? A1 is 1 3 1 by 3. A2 is 1 by 3 square. What is a3? A3 is 1 by 3 to the power of 3 and up to so on. Okay, but if you take this kind of, if this is your sequence, what will be a1? N is equal to 1 up to, say, substitute here in the last term, substitute n is 1, 3 power 1 up to 1 by 3 whole, right? Up to 1 by 3 means what? 1 plus 1 by 3. So this is first term of that sequence. A2, substitute n is 2 here. If substitute n is 2 here, what will you get? 3 square up to 1 by 3 square you have to write 1 plus 1 by 3 plus 1 by 3 square, like this. So what is a3? Substitute n is 3. Substitute n is 3, 3 power 3 up to 1 by 3 power 3. So 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 power 3. Likewise. So therefore, what is an now? Substitute n instead of, so n only up to 3 power n. Up to 3 power n means what? 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 power 3 plus up to so on plus 1 by 3 power n. Look at, this is my an only. This is my an only. Look at, this is my an. So that is the difference between this kind of sequences and this kind of sequences. Okay. I hope it is very clear. Now in today's class, we are going to discuss some convergence test. First one in this integral test. So in the last class, we did up to theorem number 4. Now theorem number 5. Okay. Let an be a sequence of positive terms. An be a sequence of positive terms. Only positive terms you have to take. That is a condition. Suppose an is equal to f of n. So I am defining the function like this. It means what? See, for example, an is 1 by n. Let's say an is 1 by n. So therefore, this 1 by n is my function of n indirectly. It is a function of n only, right? This is function of n. So now this function will take it as some f of n like this. Okay? Yeah. So where f is a, what kind of function f? F is a continuous and positive value decreasing function. So 3 conditions must be satisfied. Such f is nothing but what again? 1 by n only, such an only, right? Nth term of the sequence is nothing but your function f. So such nth term, that means such 1 by n, such functions must be continuous and positive value decreasing function. It should be decreasing function. Such kind of series, such kind of sequence only I will be considered in this integral test. For example, if I take an is equals to, let us take n. What are the terms now? 1, 2, 3, 4. It is increasing sequence, right? Such things we should not take. Because what I want to take? Decreasing function. I have to take decreasing function. Which one? F is a decreasing function. So therefore, if you take 1 by n, what are the terms? 1, 1 by 2, 1 by 3, 1 by 4 like this. So now clearly it is decreasing. Therefore, this is allowed. This kind of sequence allowed in this theorem. And not only that, it should be positive valued. Look at each and every number is a positive number. Negative numbers we should not take. For example, an is equal to minus 1 whole to the power of n by n. If I taking like this, then what is the first term? Minus 1 by n, 1. Second term, 1 by 2. Third term, minus 1 by 3. Fourth term, 1 by 4. But each term is not positive, right? So therefore, such a sequence also we should not consider. Hope it is very clear. So first f should be continuous. That means everywhere it should be well defined. F is continuous means. Okay, for example, in this sequence n is running from where to where? N is running from 1 to infinity, right? So therefore in this interval 1 to infinity, the given function must be continuous. So if the function f of n is 1 by n, for example, okay, 1 by n, whatever number you substitute from this interval 1 to infinity, this function is well defined. For example, if I take 1 by n minus 1 as my f of n, if the interval is 1 to infinity, so in this interval, if I substitute n is equal 1 here, what happens? 1 minus 1, 0, 1 by 0, infinity. It is not defined. Therefore, it is not continuous. Not continuous. Okay? Hope it is clear now. It should be continuous means at every domain point, the function should be well defined. This function should be well defined, but this function is not well defined at n is equal to 1. Because here in the sequence, n is a natural number, right? Natural number means 1, 2, 3, 4, 5, up to so on, all these things. These are natural numbers, intersection with natural numbers to take. That means in this we are having only 1, 2, 3, 4, should not be 1.1, 1.2 like that. Okay? Only natural numbers like this in this interval. Only natural numbers, because n is natural number. So you take whatever the natural number and substitute here, this function should be well defined. Then only I can say that it is continuous. Such kind of 3 entry passes required for integral test. First entry pass is it should be continuous. Second entry pass is all the terms are positive. And third entry pass is the function should be decreasing. Now, for x more than or equals to n. X more than or equals to n means for few points no need to worry about. For example, first 3 points are not decreasing. Don't worry about first 3 points. You look at from 4th point onwards. Infinitely many points should satisfy these 3 conditions. F is continuous and positive valued and decreasing function of x. Okay, these 3 conditions must be satisfied after certain stage. But how many terms need to be satisfied? Infinitely many terms need to be satisfied. That means here it is given that n is more than or equals to capital N. That means what? After capital N, that means n, n plus 1, n plus 2, all these terms. an and an plus 1, an plus 2 term like this. All these terms must be satisfied all these 3 conditions. Okay, then the conclusion is the series n is running from n to infinity an and the integral both converge or diverge together. So in this test what we are going to do is we have to find the integral value. If this integral value is finite, therefore this integral is converges, therefore automatically this series converges. If this integral value is infinity, therefore this integral is diverges, therefore this series also diverges. Like that both converge or diverge together. So instead of finding directly the convergence status of series, we are finding the integral value of the same function. If an is 1 by n, just now I told you, if an is 1 by n, what is f of n? 1 by n. So f of x is 1 by x. So integration 1 by x I need to calculate like this. If that value is finite, corresponding series value should finite. Okay. So the proof is not required. Just look at some problems related to this. Problem number 1. Prove that the series n running from 1 to infinity 1 upon n squared plus 1 is converges. So now, so far what we have seen, nth term divergence test we have seen, right? Nth term divergence test. Let me verify all those things can be applied on. First, we have seen nth term divergence test. Okay. See, now we are discussing the problem after integral test. Therefore, integral test immediately you are applying. But if the same problem comes in exam, which test you will apply? Like this you have to verify. First we are having nth term divergence test. So according to this test, what I required, limit n tends to an value should be not equal to 0 or fails to exist or fails to exist. Then what can I say? The series is diverges, fails to exist. Then the comment is the series is diverges. Let me calculate here. So what is limit n tends to infinity? An. Now what is that? 1 upon n square plus 1. Now what is this value? It is getting 0. Therefore we cannot conclude. We cannot conclude. Hope it is clear. So therefore nth term divergence test. Now here it is not working. It is not working. Next we have seen geometric series, right? Let me look at geometric series theorem. Upon n square plus 1, right? N square plus 1. Now what are the terms now? First term is 1 upon 2. Second term, substitute n is 2, 1 upon 5. Plus third term, 1 upon 10. Fourth term, 6 to 7, so 1 upon 17. Okay. Plus up to so on. So in this first term is 1 by 2, but is it geometric series? So what is a2 by a1? a2 by a1. So 1 by 5 divided by 1 by 2 is nothing but 2 by 5. Okay. Similarly, a3 by a2, a3 by a2, 1 by 10 divided by 1 by 5. What is this? 5 by 10 is nothing but 1 by 2. So these two are not same. Look at 1 by 2 I am getting here, and here 2 by 5. Therefore this series is not geometric series. Therefore this theorem we cannot apply. 2 is gone. Now we have to move on to integral test like this. So again integral test you want to verify. If it is working out, then you can apply. If it is not, then we have to move further like that. So this is a general way of checking can we apply the various techniques to the series. So look at here, I am not finding what is the sum of the series. I am not finding what is the sum of series. Question is show that it is converges. That means what? I need to show that sum is finite. What is that finite? I don't want. What is that finite? I don't want. What I want? Is it finite or not? Okay. If you look at geometric series theorem, in geometric series theorem clearly it says what is the sum exactly. Only geometric series theorem says, but not integral test. Okay. Yeah. Let me look at now integral test. Let us fulfill all the requirements. First one. So what is given to us? Series is 1 upon n square plus 1. Okay, n is running from 1 to infinity, right? So therefore what is an now? An is 1 upon n square plus 1. So this is my f of n. Okay. What I want? F of n should continuous. Is it continuous? Verify. Yes, it is continuous because you substitute all the natural numbers here. It is 1, n is 2, n is 3. Each and every number it is well defined. Therefore, it is continuous. So therefore, first one, f is continuous. F is continuous. Okay. Second one, what I want? Is it positive valued? Yes. Each and every number is positive, right? And f is positive valued. Positive valued function. Because each and every term is positive. Third condition, what I want? It should be decreasing. Is it decreasing? Verify once. So how to verify? Look at the terms, or simply use the technique an plus 1, calculate an plus 1, and an plus 1 minus an you compute. Okay. Then according to that you can find where it is increasing or decreasing. But here directly I am finding what are the terms now. What are the terms? So clearly the terms are, so let me write here itself. An is nothing but 1 upon n square plus 1. N square plus 1. What are the terms now? Substitute n is 1, 1 by 2. Next n is 2, 1 by 5. N is 3, 1 by 10. N is 4, 1 by 17, and up to so on. Okay. Now let me compute in decimals. 1 by 2 means what? So now 1 by 2, 0.5, right? 0.5. 1 by 5, 0.2. Okay, it is decreasing. Okay. 0.1 like that. So it is decreasing. So therefore, what is the comment? Therefore, sequence an is decreasing. An is decreasing. So therefore, all the conditions are satisfied. Decreasing sequence. So therefore, we can apply. Therefore, by integral test. Now we can apply integral test. By integral test, what we need to find? integration f of x dx and series an both converge or diverge together. Okay, so both. Okay, then let us find the status of integral. Okay, so therefore what I'm going to find is, so therefore integration, uh, series is running from 1 to infinity, right? Therefore here the limits also, integral limits also, you have to take 1 to infinity only. For example, if the series is 2 to infinity, this series, the given series is 2 to infinity, what I have to take? Here also integration 2 to infinity I have to take. Okay, 1 to infinity f of x dx I want. This value I need to compute first. If this is finite, then integral value should be finite. 1 to infinity. Now what is f of x here? 1 by x square plus 1 dx. Okay. Now what is this? Tan inverse x, right? Recall the formulas from your PUC. Compulsory required in this integral test. Tan inverse x, and x is running from where to where? 1 to infinity. Now what is this value now? Tan inverse infinity. Well, that is pi by 2 minus tan inverse 1 pi by 4. How much? So 90 degrees minus 45 degrees is 45 degrees. So pi by 4, and this is finite number, right? So this is finite number. So integral value is pi by 4, and this is finite number. This is finite number. So therefore the integral converges. Therefore the series also converges. The series, what is that? 1 upon n square plus 1, n is running from 1 to infinity, is also converges, because both converge and diverge together, right? Also converges. So this is a conclusion. But don't do one mistake. Let me write here note. If integration f of x dx converges to some number L, then the series an may not converge to L. That means integral value is pi by 4. I cannot say that series value also pi by 4. That is wrong. Okay, that's what I'm going to say. If integral value is some L, it doesn't mean that series value is also L, but I can say that it is converges. It converges to some different value, but not exactly same as integral value. Exactly same as integral value. That is a note. So this is very important. Remember this. Okay. In this integral test, we can tell that only status converges or diverges. That's it. At what number it is converges, we cannot say. Okay. So here I can say that the series is converges. That means what? The sum is finite number. You take infinitely many numbers. That means 1 by 2 plus 1 by 5. Look at the first term is 1 by 2, second term is 1 by 5, like that. 1 by 2 plus 1 by 5 plus 1 by 10 plus 1 by 7 up to so on. You add infinitely many terms, but the sum is finite number. What is that? We cannot tell by this test. Okay, by this test only status. Next one, continuation problem number 2. Prove that the series 1 upon n square is converges. Again same story. So roughly I will discuss. First nth term divergence test. Okay, first one, nth term divergence test. It is an 1 by n square. I am getting 0. Therefore we cannot apply. So therefore we cannot conclude. Okay. Similarly, second one. What is second one? Geometric series, right? Geometric series test. This, according to this, first I want what are the terms now. First term is 1. Second term is 1 by 4. Third term is 1 by 9. Next 1 by 16 plus up to so on. Is it geometric? So 1 by 4 divided by 1 is 1 by 4 only. Next 1 by 9 divided by 1 by 4 I want, right? 1 by 9 divided by 1 by 4. How much? 4 by 9. So it is not equal. Look at these two are not equals. Here 1 by 4 I am getting, here 1 by 4 by 9 I am getting. So since these two are not equals, therefore this is not geometric. So therefore this also cannot be applied. It is also cannot be applied. So then move on to the next available test. So the next available test is integral test. So in this integral test, what are the requirement? First one should be f should be continuous, right? First let me write what is so an is, what is an? 1 upon n square, which is nothing but f of n, which is nothing but f of n. Okay. Now first one, it should be continuous, right? Yeah, it is continuous. F is continuous, satisfied. Second one, f should be decreasing function. Is it decreasing? Continuous of positive value, right? Yes, f is positive value function. So second condition also satisfied. Now what is third condition? Third condition, f should be decreasing. So sequence a I need to write, right? Sequence an, which is nothing but sequence 1 upon n square, is nothing but, what is the first term? 1. Second term 1 upon 2 square. Third term 1 upon 3 square. Fourth 1 upon 4 square, come up to so on. So now here 1 itself 1 by 4, 0.25. So it is decreasing, right? Not to look at all these things. So therefore, clearly therefore sequence an is decreasing. Decreasing sequence. Therefore clearly by integral test. So therefore by integral test. What I want? I want first integration value, right? So therefore the integral value is is running from 1 to infinity. Therefore integration 1 to infinity f of x dx or f of n dn, whatever. So integration 1 to infinity. What is f of x? Here 1 by x square, right? Because f of n is 1 by n square. F of x is 1 by x square. Instead of n you write x dx. What is this? X power minus 2 plus 1 by minus 2 plus 1, right? You write this on the numerator, you will get x power minus 2. So what is the integration? X power minus 2 plus 1 minus 2 plus 1. So from where to where? 1 to infinity. Now what is this now? So if you simplify this, you will get minus 1 by x, right? Minus 1 by x, from where to where? 1 to infinity. 1 to infinity. Now what is this? So minus is outside. 1 by x, 1 by infinity, minus 1 by 1. And what you are getting? You are getting 1. So this is finite value. Okay. So therefore what is the conclusion now? So therefore since integral value is finite, so therefore integration 1 to infinity is converges. So therefore the series 1 upon n square, n is running from 1 to infinity, is also converges. That's it. I cannot say that series 1 upon n square is equal to 1 because integral value is 1. It doesn't mean that series value is also 1. That is wrong. I can say that only status converges or diverges. That's it. So therefore the series is converges by integral test. Next one, problem number 3. Okay, so let me do the same. Again same story. So roughly I am verifying. First one is nth term divergence test. 1 by infinity 0, so you cannot apply. Okay, nth term divergence test I cannot apply. Second one, geometric series. So what is the first? N is equal to 2 onwards, right? N is equal to 2 onwards. If you substitute n is 1 by ln1 value 0, 1 by 0 infinity. That's why I am not running series n is equal to 1 to infinity. Okay, n is 2 to infinity. Okay. So second is geometric series. Yeah, 2 into ln2. Next 3 into ln3. Next 4 into ln 4. So clearly a2 by a1 is not equal to a3 by a2. Therefore it is not geometric series also. So geometric series test also I cannot apply. So then go to the integral test. So in that integral test, first one is, so before that let me write what is an. An is 1 upon n into natural logarithmic function of n. So this is an is nothing but f of n. Okay, here n is running from 2 to infinity. Okay, so then what is the first condition? We want the function should be continuous, right? So clearly the function f is continuous. F is continuous because you have to look at only 2 to infinity only here. Okay, continuous on which interval? 2 to infinity. You substitute any number in this interval, this function is well defined. If I substitute n is equal to 1, ln1 is 0, 1 by 0 is undefined. That's why I am writing 2 to infinity. At 1 it is not well defined, that's why. So if you take the interval 1 to infinity, in this interval the function is not continuous. Because at 1 the function value infinity. Okay, that's why the series is running from 2 to infinity. Therefore I have to take 2 to infinity only the interval. Function is continuous on this interval. Okay, next second one, I want it should be second one, it should be positive value. Yeah, clearly f is positive value. Whatever the natural number is substitute from 2, it is always positive. F is positive value. Positive valued function. Valued function. On which interval? 2 to infinity only. 2 to infinity. And third one, third requirement, it should be decreasing function, right? So clearly sequence an, which is sequence 1 upon n into ln n. Now what are the terms now? First term n is 2, right? 2 to infinity out substitute, n is equal to 2. First n is 2, so 1 by 2 into ln2. Next 1 by 3 into ln3. 3 into ln3. Okay. Next up to so on. So clearly look at, so 2 into ln2 is always less than 3 into ln3, right? So if you do reciprocal, 1 by 2 into ln2 is always more than 1 by 3 into ln3, clearly. Okay, therefore this number is lesser than this number, therefore it is decreasing sequence. Okay, so therefore sequence an is decreasing sequence. Okay, so all the three conditions are fulfilled. Therefore now we can apply integral test. Compulsory 3 conditions need to be satisfied, then only we can apply integral test. If any of the 3 conditions is not satisfying, for example first 2 conditions are satisfying but third condition is not satisfied, therefore you should not apply integral test. Compulsory all 3 must be satisfied. So therefore by integral test x into ln x dx, so this value I need to compute. Okay, so now to evaluate this integral, so since ln function is present, let u is equal to some ln x. The only thing is I have to solve this integral. Okay, then what is du? Du is equal to 1 by x into dx. Both sides I am applying derivative. Okay, so du is equal to 1 by x dx. Then you modify the problem, so which is integration. So accordingly you apply upper and lower limits. Okay, so then corresponding upper and lower limits are, yes, so old limits x is equal to 2 to x is equal to infinity, right? Old limits are 2 to infinity. Now new variable u, right? So u limits. So if x is equal to, let us look at lower limit, x is 2, then what is u value? U value is ln of 2. X is 2 substitute. Therefore new lower limit is ln2. Next, if old upper limit is infinity, then what is new upper limit ln infinity is again infinity. Okay, so therefore now the integral value, so integration 2 to infinity 1 over x into ln x dx, this become integration ln2 to infinity, right? ln2 to infinity 1 by x dx. First 1 by x dx, how much? Look at 1 by x dx value is du, so let me write here du. So 1 by x dx are substituted. Next 1 by ln x value, what is 1 by ln x? 1 by u. 1 by u. That's it. Integration ln2 to infinity 1 by u du. What is 1 by u? Again, 1 by u value. What is that? ln u, right? Integration ln u. Now, what are the limits? ln2 to infinity. ln2 to infinity. This is for what? U limits, right? U limits. U is running from ln2 to infinity. Now, substitute ln of ln2. Instead of u, I am substituting ln2. Instead of u, I am substituting ln2 minus ln of, instead of u, I would substitute upper limit infinity. Now this value is finite, okay, but this value is minus infinity. So overall this answer is minus infinity. So this is not finite, okay, not finite. It is not finite. So therefore, what is the conclusion? So therefore, the integral integration f of x dx diverges. Integral is diverges. So therefore, the series what diverges. That's it. So this is example of diverges. So therefore, this series is diverges. So like this, I can conclude by using integral test. Next, one more, theorem number 6. This is P series test, another test. If integral test is fails, then we can go to the P series test. Let's look at the theorem statement. Let the P series is this, series n is running from 1 to infinity, 1 over n power p. Then run this. If n is 1, it is 1. So first term is 1. Let me write here. It is not given. So 1 power p, right? So 1 plus 1 power p. So 1 over 1 power p. 1 power. This is not given. Let me write this. Substitute n is 1 over 1 power p plus second term n is 2. So 2 power p. Third term n is 3 power p. N is 4 power p plus up to so on. Nth term is n power p plus up to so on. How many terms are there? Infinitely many terms. Okay. And this series, where what is p? P is a real constant. P is a real constant. And this P series is converges if P is more than 1, and same P series is diverges if P less than or equals to 1. So I will give the proof for this. Look at carefully. It's a simple one. Yeah. So first you write the given series. So series 1 upon n power p. What is p now here? P is real constant, right? P is real constant. Okay. So therefore, what is an now? So therefore, an is 1 upon n power p. This is an. Okay. Yeah. Now first one is, I need to prove that the series is converges, the P series converges if P more than 1. So therefore, let P more than 1 you write. First I'm starting with P more than 1. Then I have to prove that it is converges. If P is more than 1, then do the calculations. So therefore, clearly, what I can say, therefore an, which is 1 over n power p. See, p is more than 1, right? Therefore, this power is always positive. If power is always positive, look at this one. I am calling this function is some f of n. So first condition, f is continuous. F is continuous. From where to where? On 1 to infinity. On 1 to infinity. Whatever the number is substituting that in this interval, it is well defined. Second one, what I want to apply in the integral test. If p is more than 1, this n remains in the denominator only. If p is negative, for example, if p is negative, what happens? N power, let me write minus 1. Then it's nothing but n only, right? But this is increasing sequence. This is nothing but increasing sequence, right? 1, 2, 3, this is increasing sequence. P is negative here, but here I have taken let p is positive, right? If p is positive, more than 1 particularly. So therefore, it is always in denominator only. So therefore, I can say that f is decreasing. F is decreasing. F is decreasing function. Okay. Next, third condition is f is positive valued clearly. F is positive valued because negative values will not get. f is positive value of the function. So therefore by integral test, so therefore nothing but 1 to infinity. What is f of x? 1 over wherever n, there you write x power p dx. Remember p is more than 1 in this case, first case. Okay, in this p is 1 I am taking. So let me write these are a, b and c. Let me write like this because already 1, 2, 3 I am using. Don't get confused. ABC. So now this is, yeah, let me compute these values. So what is this? X power minus p, right? So x power minus p plus 1 by minus p plus 1. And the limits are from where to where? 1 to infinity. Okay. Now 1 over 1 minus p is out. I am writing this one outside. And x power 1 minus p. And the limits are where to where? X is running from 1 to infinity. X is infinity. And these limits you have to apply. Okay. Look at. So 1 over 1 minus p. And after applying the limits, what will get? So yeah, apply the limits here. Look at, substitute upper limit is infinity, so infinity power 1 minus p, right? So infinity power 1 minus p minus next one 1 power 1 minus p, right? So 1 power 1 minus p. Yeah, now here we need to investigate. Here p is more than 1, what will be 1 minus p value? So 1 minus p value how much? If p is more than 1, let me write here. If p is strictly more than 1, then send p to this side. So 0 more than 1 minus p, right? P I am sending this side. Or both sides I am subtracting p. Okay, so 1 minus p is less than 0. So therefore 1 minus p is less than 0. That means what? It is negative. So therefore look at this power, infinity power. 1 minus p is negative. Let's say for example negative means minus 2 for example. So if infinity, look at here, let me write here, infinity power some negative number. What is this? 1 by infinity square, right? What is this? 0 only. So if the power is positive, for example, let's take infinity. Let's take 2, positive, power is positive. Infinity square is infinity only. Okay, so if the power is negative, then I will get 0, finite value. So clearly this power is negative. So therefore what I can say? So therefore 1 over 1 minus p. What is the infinity power 1 minus p value? 0, because 1 minus p is negative. Minus 1 is nothing but 1 over p minus 1. So therefore this is finite value. Okay, this is finite value. What is p? P is a real constant, right? So that is finite. So finite number. So this is finite number. Therefore, what I can say? Conclusion. So therefore, the integral converges. The integral converges. So therefore, the series also converges. What series? Particularly p series. The p series also converges for what? For p strictly more than 1. So first proof is over. Next you look at second statement. If p is less than or equal to 1, right? So if p less than or equal to 1, I need to prove that it is diverges. So let me write. Yeah. Yes. So next one, case 2, that means second statement. Let us take if p is less than 1 first. Less than 1 let me take. Next equal to 1 I will take. Okay, if p less than 1. Now let us go to the calculations. So you find the integral value. So integration f of x dx. Nothing but integration 1 over x power p dx. What is this? If p less than 1, So already we calculated this is integral value, right? This is integral value. Let me write this directly. It is 1 over 1 minus p. Okay, 1 to infinity, 1 to infinity. Yeah, 1 over 1 minus p. So infinity power 1 minus p minus 1 power 1 minus p. Now in this, if p less than 1, so let me write here. So if p less than 1, p less than 1. So therefore clearly then bring p to right hand side. So 0 less than 1 minus p. That means 1 minus p is positive. If you look at the power, infinity power is positive. Then what is this calculation? So 1 over 1 minus p. Now what is this value? Infinity only. 50 minus 1. So answer is infinity. Plus or minus infinity depending upon p value, right? If p is more than 1, for example, p less than 1, right? So if p less than 1, then 1 minus p value is positive. Therefore, plus infinity I can write here. So this is plus infinity. Plus infinity. So therefore, the integral diverges, right? So therefore, integral f of x dx diverges. Dx diverges. So therefore, series 1 over n power p also diverges. Okay, this is p less than 1. If p is equal to 1 case, so p is equal to 1, in this calculation if p is equal to 1, 1 minus 1 0, infinity power 0 is undefined, and here also if p is 1, what happens here? Look at this one in this calculation. So 1 over in this calculation, look at in this, I'm substituting p is 1, so 1 minus 1 0, 1 by 0 is infinity into undefined is again undefined. That's why I'm not writing less than or equal to 1 here. Just have written p less than 1. So next you write in this only, p is equal to 1 case you prove. If p is 1, directly you substitute here. P is 1, then 1 by x. What is 1 by x value? ln x. Let me do here. Okay. Yeah, let me do here. So if p is 1, if p is equal to 1, then integration 1 over x power p dx is equals to integration 1 over x dx. From where to where? 1 to infinity. Okay. This is ln x from 1 to infinity. 1 to infinity. This is nothing but ln infinity minus ln 1. Minus ln 1. But ln 1 is 0, but ln infinity is infinity. Look at. Therefore integral diverges. Therefore series diverges. Therefore overall, what I can say? The series is diverges for p less than or equal to 1. And the p series is converges if p strictly more than 1. So proof is over. Next let us do some problems related to the p series. Look at problem number 4, which is nothing but problem number 2 only. Already I have done this problem by using which test? Integral test already I have done. Let me do it by using this test. Okay, p series test. So according to p series test, if p is, look at, is it exactly in that format or not? You have to verify first. Look at, is exactly in that format only, right? So the series 1 upon n raised p, this n raised p where n is running from 1 to infinity, and this series is converges, this series is converges if p is more than 1, and diverges, just now we proved, diverges if p less than or equals to 1. This one you proved just now. So therefore according to this statement, look at exactly this one is in that format only, right? 1 over n square. So instead of p, what you are having? 2. So therefore what we can say? So therefore by p series test, we have p is equal to 2 here, which is nothing but which is more than 1. So therefore the series 1 upon n square where n is running from 1 to infinity is converges. That's it, directly. I want only status. I am not asking what is the sum. Look at, prove that the series is converges. Question is find the what is the sum. Question is not like that. Question is not the question is not about what is the sum. Question is only what is the status of the series. Is it converges or not? Prove that the series converges. Yes, the series is converges. That's it. So how simple it is compared to integral test. So P series is easy, right? Yeah. Next one, similarly, problem number 5. Now look at this one. Find the convergence status of this harmonic series. So it is a special name for this series. The name is harmonic. This series is said to be harmonic series. Okay. Now, so again same story. Solution. So by P series test, by P series test, by P series test, we have n is equal to 1, right? So therefore series 1 upon n is running from 1 to infinity. So for p is sorry n is, we have p is equal to 1 here, right? We have p is equal to 1 here. So we have p is equal to 1. So therefore is diverges, because p less than or equal to 1, the series diverges. That's it. The series is diverges just by P series test. Next one is logarithmic P series test. Next one, logarithmic P series test. So this is a logarithmic P series. So series n is running from 2 to infinity, 1 over n into ln n whole power p. Exactly, it should be in this format only. Then only we can apply this theorem. Otherwise, we should not apply this theorem. Compulsory, the series should be in this format only. What is p? P is a real constant. Now let us run the series. N is starting from where? 2, right? So now substitute n is 2. 2 into ln 2 whole power p. Next substitute n is 3. Look at 3 into ln 3 whole power p. 4 into ln 4 whole power p. The power p is only for ln, not for n. That you have to understand here. The power p is only for ln only, larger function only, not for n. Again, this series is converges if p more than 1, and the series is diverges if p less than or equal to 1. So same like this, you take proof, take it exercise. Once you try, I will do in next class, but you try once. Okay, again same story. First one, let p is more than 1 you take, then start doing this. So an is 1 upon n into ln n whole power p. Okay, then you take this one is ln n an, which is f of n you take. By using integral test, you prove it. 3 conditions. If it is verifying, then apply integral test. According to integral test, again same story. What I have done there, infinity power 1 minus p. Then I counted what is the sign of 1 minus p. Accordingly, I calculated what is integral value. Same story here for logarithmic P series test. You try once, definitely will get it. If not, I will do in next class. And with this, I will stop.